We have spent this whole season under the hood. The engine that runs the model, the cache that speeds it up, the training that shapes it, the microscope that reads it. So let us end with the most honest question of all. What is still broken? It is tempting to imagine the frontier as a fixed list, a wall of things AI just cannot do. But that picture is wrong, and it is wrong in a useful way. The real frontier is not a wall. It is a coastline, jagged, uneven, brilliant in one inlet and stuck in the next, and for the first time we can actually measure its shape. And here is the twist that ties the whole season together. The most stubborn failures are not failures of magic. They are failures of incentives and of measurement. Today we chart the coastline honestly, and then we look at what is genuinely coming next. Start with the famous one. Models still make things up confidently, and we covered the mechanism back in Season 1. So I am not going to rederive it. I want to ask the deeper question the field finally got a clean answer to in 2025. Why does it persist, even as everything else gets better? Part of the answer is just mathematical. You can prove that a model which freely generates statements must make at least about twice the errors of a much simpler judge that only has to check whether one finished statement is valid. Generating is harder than checking, so some error is statistically baked in. You cannot drive it to zero, but that floor is small, and it is not why hallucination stays so stubborn. The real reason is the part that should bother you. We accidentally trained models to guess. Picture a multiple-choice exam where leaving a question blank scores 0 and a wrong answer also scores 0. On a question you genuinely do not know, what is the rational move? Guess. You have nothing to lose and everything to gain. Now here is the uncomfortable fact. Almost every benchmark we rank these models on is scored exactly like that exam. A confident wrong answer and an honest I do not know are graded the same, and since I do not know earns nothing, it is never the winning move. We built the leaderboards, and our leaderboards reward bluffing. So the fix is not a bigger model. It is a better exam. Score honesty. Put a penalty on a confident wrong answer. Give real credit for a well-calibrated I do not know, and the rational move flips. The incentive arrow rotates from guess toward abstain. That is the live frontier right now. Not erasing hallucination, which the math says you cannot fully do, but changing what we reward so a model is no longer punished for being honest about the edge of what it knows. Here is a smaller mystery that hides a beautiful lesson. Set the temperature to 0. That is supposed to mean no randomness. The model always picks the single most likely next word. So the same prompt should give you the same answer every single time, bit for bit. It does not. Run it twice and you can get two slightly different outputs. For years the folklore blamed tiny floating point errors on the chip, just unavoidable hardware noise. That explanation is incomplete, and the real reason is far more interesting. It is not your request at all. It is everyone else's. When you send a prompt, the server does not run it alone. It bundles your request into a batch with other users who happen to arrive at the same moment. And the size of that batch quietly changes the order in which the math gets added up inside the chip. Now, adding numbers on a computer is not perfectly associative. A plus B plus C can land on a hair different result than C plus B plus A in the last decimal. So the same prompt, in a batch of 8 versus a batch of 80, takes a slightly different numeric path, and once in a while that hair of difference tips which word comes out on top. Your answer depended on the strangers standing next to you in line, and because we understand the cause, we can fix it. You can write the math so it adds up in the same order no matter the batch size, what researchers call batch invariant kernels, and you get bitwise identical output every time. It just costs you, running roughly 1.5 to 2 times slower. Reproducibility, it turns out, has a price. Now the big one, and this is where the season comes together. Back in Season 2, we proved a hard truth about long tasks. If a model is 95% reliable on a single step, then over a chain of 50 steps its success rate is 95% multiplied by itself 50 times, which collapses to under 10%. Reliability compounds, and it compounds against you. That was the math. Now we have the data, and it is stunning in both directions at once. Researchers measured what they call a task time horizon, the length of a job, measured by how long it takes a skilled human, that a model can finish with 50% success. Plot that horizon over roughly the last 6 years and it doubles, remarkably steadily, about every 7 months. Seconds-long tasks became minutes, minutes became hours. And the most recent updates suggest the pace has picked up, with the doubling closer to every 4 months lately, though over a shorter window, so hold that newer number more loosely. On a steady exponential, that is the optimistic story, and it is real. But now hold it against the Season 2 math, because the very same researchers measured the catch. Raise the bar from 50% success to 80%, the kind of reliability you would actually need to leave a model alone with a job, and the horizon you can trust shrinks to very roughly 1/5 of its length. That is our compounding curse, made measurable. A model can attempt a long task. Trusting it to actually finish one unattended is a far shorter leash. And when a separate team, at scale AI together with a safety research center, took real freelance projects that people genuinely got paid to do and measured how many an AI agent could complete start to finish, the automation rate came out around 2.5%. So hold both truths at once. The capability curve is climbing fast and it is not slowing down. And reliable, paid, real-world autonomy is still, today, a thin sliver. That gap between what a model can attempt and what you can trust it to finish on its own is the most important number on the whole coastline. So that is what is broken, honestly. What is actually coming next? Everything we have built this season learns from text, an ocean of human writing. But text is a shadow of the world, not the world. A child learns that a dropped cup falls before they can read a single word. They learn it by watching, by poking, by living inside physics. So a growing camp of researchers is making a different bet. Instead of only predicting the next word, build a model that predicts the next moment of the world. Feed it video and interaction, and have it learn an internal simulator. What happens if I push this? Where does the ball roll? What is behind that door? These are called world models. Some can already generate an interactive scene you can move through, frame by frame. Others build a navigable three-dimensional space from a single photo. And one of the field's pioneers argues that the path forward is not to predict every pixel, which wastes effort on noise, but to predict in a space of meaning, learning the structure of the world the way the embeddings we have studied capture the structure of language. Now I have to be careful here, because this is exactly where hype lives. World models are not a proven replacement for language models. They are a contested, complementary bet, a different way to learn that might fill in the physical common sense that text alone leaves thin. The honest statement is that nobody knows yet which path, or which blend of paths, leads furthest. And whatever you have heard about a fixed date when machines match us at everything, treat it as a claim by the person making it, not a measurement. One more piece of honesty, because you will hear the opposite. The models we have are not quietly rewriting their own minds while you sleep. Once training ends, their weights are frozen. When a system seems to remember you across chats, that memory lives outside the model. In a notes file, the system feeds back in, not in the weights themselves. Making a model truly learn on the fly, updating its own weights from experience, is an open research problem with early prototypes, not something running in the products you use today. So no, it is not self-improving in the wild. What it is doing is being measured, openly, on a coastline we can finally chart. And that, more than any single capability, is the real progress. So that is the honest frontier. Hallucination persists not because the model is stupid, but because we built exams that reward a confident guess over an honest I do not know, and the fix is to score honesty. The strange flicker at temperature 0 is not magic. It is the batch of strangers sharing your computation, and we can lock it down when we choose to pay for it. The capability curve is climbing fast, doubling its reach roughly every 7 months, while reliable real-world autonomy stays a thin sliver, because reliability compounds against long tasks exactly as the math warned. And the next chapter may not be a bigger language model at all, but a different kind of model that learns the world by watching it move. Look back at where this season started. We treated the model as a black box and learned to read its mind. We followed a single token through the engine, watched training carve knowledge into frozen weights, and learned to measure exactly where it succeeds and fails. The point was never to worship the machine and never to dismiss it. It was to see it clearly. A grown mind we are only beginning to understand, brilliant and brittle in ways we can now actually chart. The frontier is not a wall. It is a coastline. And for the first time, we have the instruments to map it honestly. That is how AI works under the hood.